Hello, this is Richard Hammock's Calculus 1. We are in part 4 of the course on applications of derivatives. Today, lecture 32A. The topic is concavity and curve sketching. We begin with a roadmap of where we are and where we are going in part 4. Remember, our goal, our destination, is to understand the behavior of a function f of x. And our approach, the road we're taking, is to use derivatives as tools to understand f of x. In lectures 30 and 31, we asked the question, what does f prime of x tell us about f of x? And we found that f prime tells us about the increase-decrease of f. F of x increases where f prime of x is positive, and f of x decreases where f prime of x is negative. In lectures 32a and 32b, the question is, what does f prime prime, the second derivative, tell us about f of x? And as we'll see today, it tells us something that's called the concavity of f of x. And we're going to further use this knowledge to help sketch graphs of functions. So today's topic, concavity. There are two basic shapes that a graph of a function, or maybe a part of a graph of a function, can have. On one hand, we say f of x is concave up if the graph looks like this, if it looks like a bowl that would hold water. And we're going to say that f of x is concave down if it looks like an upside down bowl that would dump water out. And here's an example. I've got a function f of x graphed here, and we would say this particular function is concave up on the interval from 1 to 2, because if you look at that interval from 1 to 2, the graph looks like this, and that's basically the concave up shape. We would say f is concave down on the interval from negative infinity to 1, because on that interval, the graph looks like part of an upside down bowl. It looks like this, the concave down shape. And also, we would say f is concave down on the interval from 2 to infinity. This interval, because there, the graph has the shape of an upside down bowl, like this. It's concave down. One further definition, we're going to say that a point A, f of A, on the graph of f of x, where concavity changes, is called an inflection point. So for example, this point right here, the concavity changed from concave down to concave up. That's an inflection point. And this point right here, 2f of 2 on the graph of f, concavity changed from concave up to concave down at that point. So those 2 points on the graph of f are called inflection points. I want to point out that concave up and concave down is independent from increasing and decreasing. To illustrate that, think about the shapes in this grid. The first row is a concave up shape. This is concave up, and I've got it so it's increasing. You're concave up, you have this basic shape, and we're an increasing function. So you can be concave up and increasing, but notice you can also be concave up and decreasing. Here's a decreasing function, and it's got that concave up shape. In the second row, I have pictures of concave down graphs. Both of these segments of graphs are concave down, but the first one is increasing and the second one is decreasing. So we have 4 basic combinations of increase, decrease, and concave up and down, as indicated in this grid. For example, in this function f of x, we're increasing in concave down, then increasing in concave up, then increasing in concave down, and then decreasing in concave down. I'm now going to tell you about how concavity is determined by the second derivative of f. And let's begin by thinking about a concave up function, f of x, as indicated here. I want you to think about the derivative of this function, which tells us the slopes of tangents. Starting out right here, the tangents have negative slope. They lighten up. Right there, the slope has turned into 0, and suddenly the slopes are positive, getting steeper and steeper and steeper. So f prime of x, the derivative of f, which gives the tangent slopes, starts out negative, and right there at c, it turns positive and gets bigger. The graph of f prime of x looks something like this. It's an increasing function. And we know something about increasing functions. If a function is increasing, its derivative is positive. So here we have a function f prime of x that's increasing. So its derivative, which is f prime prime of x, has to be positive. So notice that concave up, f of x, is signaled by the second derivative being positive. By contrast, think of concave down, as indicated here. The tangent slopes start out positive, and they become less and less steep until they have slope 0 right there, and then they become negative, becoming steeper and steeper and steeper in the negative direction. So f prime of x, which gives those slopes, starts out positive, it turns 0 at c, and then it gets negative. It looks like this. F prime of x is a decreasing function. And one thing we know about decreasing functions is that their derivatives are negative. So the derivative of f prime, which is f double prime of x, is negative. So we see here in this picture that the concave down shape is signaled by a negative second derivative. So here's the takeaway. For concavity, a function f is concave up, where its second derivative is positive, and it's concave down, where its second derivative is negative, as we see in these pictures. So whereas the first derivative tells us the increase-decrease of a function, the second derivative is telling us its concavity, concave up or concave down. Let's illustrate this with an example. Find the intervals on which the function f of x equals 2x cubed minus 3x squared plus 5 is increasing, decreasing, and also the intervals on which it's concave up and concave down. Let's begin with increase, decrease. We already know how to do that. To find where f is increasing or decreasing, look at its derivative, 6x squared minus 6x. And we want to find the critical points. So we factor that and set it equal to 0. And you can see the critical points of f are going to be x equals 0 and x equals 1. So those two critical points of f, 0 and 1, divide the domain of f into 3 intervals as indicated here. And then we want to look at the sign of f prime on those 3 intervals. And to do that, we can break f prime up into its 2 factors and look at them independently. The 6x is positive when x is positive, and it's negative when x is negative. The x minus 1 is positive if x is greater than 1, and it's negative when x is less than 1. So the derivative f prime, which is the product of those 2 factors, on the rightmost interval is positive times positive, so it's positive. On the middle interval, it's positive times negative, so f prime is negative. And on the leftmost interval, f prime is negative times negative, so it's positive. So we can see here an answer for increase-decrease. F increases where its derivative is positive on the interval from negative infinity to 0, and also on the interval from 1 to infinity, and it decreases where its derivative is negative on the interval from 0 to 1. So that answers the question for increase-decrease. And we already knew how to do that. Let's now turn to concavity. Where is this function concave up and where is it concave down? We learned today that concavity is determined by the sign of the second derivative. So we need to compute the second derivative, the derivative of 6x squared minus 6x. So f prime prime of x is 12x minus 6. We are now going to do with the second derivative exactly what we did with the first derivative. We'll find out where it equals 0, and that will break up the number line into intervals, and then we'll look at the sign of the second derivative on each of those intervals. So where is f prime prime of x equal to 0? You can just look at this linear function. If x is 1/2, that makes 12x minus 6 equal to 0. So you might think about that 1/2 as being a critical point for the function f prime of x. It's a number that makes its derivative equal to 0. So just one number, 1/2, makes the second derivative equal to 0. And we're going to plot that 1/2 right there, right between 0 and 1. And now we're going to look at the sign of f prime on the two intervals that number 1/2 splits the line up in. So let's see. What's the sign of f prime prime of x, which is 12x minus 6? Well, you can see that if x is greater than 1/2, 12x minus 6 is going to be positive. And if x is less than 1/2, 12x minus 6 is going to be negative. So now we can see where the second derivative is positive and where it's negative. It's positive on the interval from 1/2 to infinity. So the graph of f is concave up on that interval. And f prime prime is negative on the interval from negative infinity to 1/2. So that's where the function f, the original function, is concave down. Summarizing, f is concave up on the interval from 1/2 to infinity, and f is concave down on the interval from negative infinity to 1/2. And that answers our questions. We found out the increase-decrease of this function and also its concavity. If you were to draw a graph of this function f of x, it would look something like this. You'll notice that here it's concave down and increasing. Increasing because its derivative was positive, and concave down because the derivative is negative. And here it's decreasing and concave down. The derivative is negative, and also the second derivative is negative, and so on. Right here at x equals 1/2, that's where the concavity changes from concave down to concave up. So that's an inflection point right there, where the concavity changes. Let's do another example. Let's sketch the graph of the function f of x equals ln of x squared plus 1. And by sketch the graph, I mean we'll find out where it's increasing, decreasing. We're going to find out where f of x is concave up, concave down. Maybe look at the local extrema and the inflection points, and draw the graph of f informed by all of this information. So first of all, let's think about the domain of ln of x squared plus 1. Whatever x is, you square it, add 1 that's positive, and you can take the ln of that. So the domain of f is all real numbers, the interval from negative infinity to infinity. So maybe we'll start with a coordinate axis going from negative infinity to infinity, or at least as much of that as we can put into the picture. And now we'll think about increase, decrease. For increase, decrease, we have to look at the derivative f prime of x. Now we know from our derivative rules, the chain rule and so on, the derivative of ln of x squared plus 1 is 2x over x squared plus 1. It's the derivative of x squared plus 1 divided by x squared plus 1. And That's easy to think about the sign of because the sign is entirely influenced by the numerator, 2 times x. The denominator, x squared plus 1, it's always positive. That 2 times x is going to be positive when x is positive and negative when x is negative. And the denominator is always positive. So f prime of x is positive when x is positive and negative when x is negative. So let's tally that down here. Here's f prime of x, positive when x is positive, negative when x is negative. So you can see there that we now know that f is increasing on this interval and decreasing on that one. And right there at x equals 0, the derivative changes from negative to positive. So we know we have a local minimum by the first derivative test right there at x equals 0. And what is f of 0? F of 0 would be ln of 0 squared plus 1. It would be ln of 1, which is 0. So f of 0 is 0. Right there is a local minimum. So we're going to plot that point and go on with the rest of the graph. We need to look at concavity. For concavity, we know we have to look at the second derivative, the derivative of f prime. F prime is a quotient, so we have to use the quotient rule to compute f prime prime. It's the derivative of 2x, which is 2, times x squared plus 1, minus the top function 2x, times the derivative of x squared plus 1, which is 2x plus 0, all divided by x squared plus 1 squared. And we've got to look at the sign of this. Where is it positive? Where is it negative? So we better simplify that. Let's distribute the 2 into the parentheses. And then here, the minus 2x times 2x is a minus 4x squared. And we get some combinations, some like terms here. The 2x squared minus 4x squared is minus 2x squared. So there's some simplification there. Now, remember, we want to find out where f prime prime is positive and where it's negative. So we probably want to factor this thing as much as we can. A 2 factors out of the numerator. So on the top, we get 2 times 1 minus x squared. And that 1 minus x squared is a difference of 2 squares. So let's factor that. And now we have our second derivative totally factored as far as it'll go on the numerator and the denominator. So we need to look at where f prime prime of x is 0 and where it's positive and where it's negative. Let's start to tally that information down here, just as we did for f prime. So I have f prime prime of x equals what we computed it as here. And first of all, think about where f prime prime is 0. You can see that it's 0 when x is equal to 1, which makes this factor 0, and also when x is equal to negative 1, which makes this factor 0. So let's put dotted lines there at negative 1 and 1. And we've now divided the interval, the number line, into 3 intervals, here, here, and here, that are punctuated at negative 1 and 1, where the second derivative is 0. So we want to know where's the second derivative positive and where's it negative. Well, let's see. Let's take the rightmost interval from 1 to infinity. You might want to take like a test point of 2 and plug that into f prime prime and see what you get. F prime prime of 2 is 2 times 1 minus 2 times 1 plus 2 divided by a positive number down here. So that's a, let's see, a 1 minus 2, that's negative. The 1 plus 2 is positive. So we had positive times positive over positive. And that's negative. So f prime prime is negative on the rightmost interval. Now let's look at the middle interval between negative 1 and 1. 0 is a good test point. Do f prime prime of 0. That's 2 times 1 minus 0 plus 1 plus times 1 plus 0 divided by 0 squared plus 1 squared. That's positive times positive divided by positive, which is positive. So good, f prime prime is positive on this middle interval. For the leftmost interval, take a test point of -2 and plug it into f prime prime. F prime prime of -2 is 2 times 1 minus minus 2, and that's positive, times 1 plus minus 2, and that's negative, divided by this positive number. So positive times negative divided by positive is negative. So you can see here that our function f is concave down on this interval where the second derivative is negative. It's concave up on this next interval where the second derivative is positive. And then it's concave down again. And there are two places where concavity changes, at -1 and also at x equals +1. So you're going to have inflection points at each of these two x coordinates. So let's actually plot those inflection points, since our aim here is to sketch the graph of f of x, and the inflection points are, after all, points on the graph of f of x. So let's do f of 1. F of 1 would be ln of 1 squared plus 1, or ln of 2. And ln of 2 is about 1.7, so it's about right there. There's the point 1, f of 1. And then f of -1 would be ln of -1 squared plus 1. That's also ln of 2. So we'll plot that point right there. So we have, so far, 3 points on our graph of f of x plotted. This inflection point, this other inflection point, and remember, this point here, that's a local minimum. Let's now start hanging the graph of f of x onto these points based on the increase, decrease, and the concavity. First of all, look at this interval from -infinity to -1. We saw that f is decreasing and it's concave down because both its first and second derivatives are negative. Now, decreasing concave down would look something like that. So let's draw that in. That's our first part of the graph of our function y equals f of x. Let's move on to the next interval. From -1 to 0, you'll notice that f is decreasing and it's concave up. And it goes from this point to that one. So decreasing and concave up would look like that. Our next interval is from 0 to 1, where both f prime and f double prime are positive. So our f is increasing and concave up on that interval, and it goes from this point to that one. So increasing and concave up looks like this. And finally, this last interval from 1 to infinity, f prime is positive, so f is increasing. F double prime is negative, so f is concave down. And it starts at that point, it's going to be increasing and concave down. That would look something like that. So there's our graph. From looking at the increase, decrease, and the concavity, and also the local extrema and the inflection points, we were able to draw a very credible sketch of the graph of this function. Now, admittedly, today we have graphing utilities. Sometimes if you want to sketch the graph of a function, you just use the graphing utility. However, you know from experience that sometimes it's hard to tell exactly where the inflection points are and the local extrema from just looking at a picture on a calculator. Working things this way gives a very quick, very accurate sketch of the graph of a function. And there are going to be times in this class where that's useful to do. That's it for today. We've learned that the sign of f prime tells where f is increasing or decreasing, and the sign of f double prime tells where f is concave up or concave down. And we've used that information to draw very credible sketches of graphs of functions. Next up, in lecture 32b, we'll talk about what's called the second derivative test. And this is an alternative to the first derivative test, but it uses the second derivative instead of the first derivative. And it follows from the topics that we've discussed today. I'll see you then. Goodbye.